Have you ever wondered how the apps on your phone or the software in your car actually work? Hello and welcome to this video on software engineering. From the moment you wake up and check social media, to the time you drive home using GPS navigation, software is everywhere. We live in a world powered by software, and behind every piece of software there's a team of professionals making it all possible. This is where software engineering comes in, the discipline of creating reliable and effective software solutions. In this video, we'll explore what software engineering is and why it's so important in our modern world. We'll walk through the software development lifecycle to see how software is planned, built, tested, and improved over time. We'll also look at some of the key tools and techniques software engineers use every day to do their jobs. Finally, we'll discuss the career opportunities in software engineering and how you could be part of this exciting, ever-evolving field. Whether you're a student thinking about your future, a professional considering a career switch, or just an avid learner curious about technology, this video will give you a solid introduction to software engineering. So, let's dive in and see how software engineering touches virtually every aspect of our lives and drives the technology we use daily. The importance of software engineering. Software is everywhere, and software engineering ensures that all this software works as intended. Virtually every aspect of our lives is touched by software in some way, from the apps on our phones and the programs that run our cars, to the systems behind banking, healthcare, and entertainment. Because software is so deeply embedded in modern life, it's critical that this software is reliable, efficient, and secure. Software engineering is the field that makes sure these qualities are met by applying engineering discipline to software development. Consider how much we rely on software every day. Your smartphone's operating system and apps, the navigation system in your car, the traffic lights on your commute, and even the appliances in your home, like smart thermostats or washing machines, are all controlled by software. In fact, a typical modern car might run on over 100 million lines of code controlling everything from engine timing to braking systems. This incredible complexity is why we need rigorous software engineering practices. A small glitch in one of those millions of lines could have serious consequences. For instance, software errors in critical systems have led to major failures in the past. A famous example was the Ariane 5 rocket launch in 1996, which was lost due to a software bug only 37 seconds after launch, resulting in a loss of over $370 million. Mistakes like these highlight why careful design, testing, and maintenance are so important. Beyond preventing disasters, software engineering is also about enabling innovation and progress. Software engineers are the people who turn new ideas into reality, whether it's building a revolutionary app or developing software that can help doctors diagnose diseases. They solve complex problems and create tools that make our lives easier or our work more productive. For example, in businesses, well-engineered software can automate repetitive tasks and improve efficiency, allowing humans to focus on more creative or complex work. In science and research, software engineers develop programs that analyze data or simulate scenarios that would be impossible to do by hand. Security is another crucial aspect. In today's world, cyber threats are a big concern, and software needs to be built with defenses against hacking and vulnerabilities. Software engineering principles include writing secure code and regularly updating software to fix holes. When you do online banking or send a private message, you trust that the software guards your data. That trust exists because software engineers have implemented robust security measures behind the scenes. Finally, software engineering makes sure that software can scale and perform under pressure. Think about popular websites or apps that handle millions of users at the same time. Engineers must design those systems so they remain fast and don't crash when demand spikes. If a social media platform or an online classroom tool fails during a critical moment, it can disrupt communication for millions of people. By using well-established engineering techniques, software engineers ensure that even as user bases grow, the software remains stable and responsive. In summary, the importance of software engineering lies in quality and impact. It's what allows us to depend on technology in our daily lives without constantly worrying about it failing. From safeguarding the integrity of an airplane's navigation software to creating the next breakthrough mobile app, software engineering underpins the reliable, innovative, and secure software systems that drive the modern world. The software development life cycle. When software engineers set out to build a new software application, they typically follow a series of steps known as the Software Development Life Cycle, SDLC. The SDLC is essentially a roadmap for how to take an idea and turn it into a working software product. It's a structured process that guides the development of software from start to finish, ensuring that the end result is high quality, meets user requirements, and is delivered on time. While there are different models of SDLC, most models include similar fundamental stages. Here are 7 common stages of the SDLC. 1. Planning and requirements analysis. In this initial stage, the team figures out what needs to be built and why. This involves talking to stakeholders or potential users to gather requirements, essentially, a wish list of what the software should do. The feasibility of the project is also evaluated. Good planning sets a clear direction and scope for the project. For example, if we were creating a mobile banking app, the requirements might include features like account balance display, money transfer, bill payments, etc., and planning would determine resources and a timeline for delivering those features. 2. Analysis. This stage often goes hand in hand with planning. Here, the vague ideas from the planning stage are analyzed in detail and written down as a formal software requirement specification, SRS. The SRS is like a blueprint that precisely defines every aspect of the software, what features it will have, how it should behave, and any constraints. By the end of this stage, everyone involved should clearly understand what the software will do and what it won't do. 3. Design. Once the requirements are clear, engineers move on to designing the software's architecture. In the design phase, they decide how the software will work internally. This includes choosing the overall structure of the system, breaking the system into components or modules, and designing the database if one is needed. The design could involve creating flowcharts, diagrams, or prototypes that map out the solution. Continuing our banking app example, the design phase might specify things like how the user interface will be laid out, what the back-end system architecture will look like, how data will flow between the app and the server, and how security measures will be implemented. 4. Implementation. This is the stage where the actual code gets written. Software engineers take the design documents and translate them into a working program using programming languages. This phase is usually the longest, because writing and debugging code can be complex. Developers often use tools like code editors and compilers, and they follow best practices to make the code readable and maintainable. In team environments, version control systems are used to manage code changes, so multiple developers can work together without overwriting each other's work. By the end of the implementation stage, you have a functional piece of software. 5. Testing. Testing is a critical step that actually goes hand in hand with coding. In practice, engineers don't wait until all the code is written to start testing, they test as they build each piece. However, once a substantial part of the software is ready, dedicated testing is performed to catch any bugs or issues. Testers run the software in various scenarios to ensure everything works according to the requirements. They look for bugs, errors, or things that were missed. Different types of testing are used, for example, functional testing to check if features work, performance testing to see if the software runs fast under load, and security testing to ensure data is safe. If problems are found, the development team fixes them and tests again. The goal is to iron out as many issues as possible before the software is released to real users, so that users have a smooth experience. 6. Deployment. After testing is satisfactorily completed, the software is delivered to users. Deployment can mean pushing an update to an app store, installing software on client servers, or launching a website to the internet. Sometimes deployment is done in stages to ensure everything goes smoothly. In our banking app scenario, deployment would involve publishing the app on the iOS App Store or Google Play Store and making it available for people to download, or deploying the back-end services on the bank's servers or cloud infrastructure. 7. Maintenance. The life cycle doesn't end when the software is out in the world. In the maintenance phase, engineers monitor the software for any issues that pop up and continue to improve it. This includes fixing any new bugs that users discover, making performance improvements, and adding new features or enhancements over time. Maintenance is vital because requirements can change, maybe users request a new feature, or maybe changes in technology require updates to the software. Good software engineering recognizes that software is never truly finished, it evolves. For instance, once our banking app is in use, we might find we need to update it to support new types of phones, or add a feature like mobile check deposit in a later version. Maintenance ensures the software remains useful and reliable over the long term. These stages collectively ensure that software development is systematic and quality focused. Different organizations might name the stages slightly differently or sometimes merge certain stages, but the core ideas are the same. Waterfall versus Agile. It's worth noting that there are different ways to go through the SDLC. In a traditional waterfall model, these stages happen one after the other in sequence. For example, first complete all planning, then all design, then all coding, and so on. The waterfall approach means you try to get everything right in each stage before moving to the next. This works for some projects, but it can be inflexible if requirements change late in the game. On the other hand, many teams today use an Agile approach. Agile is more iterative and flexible. Instead of doing one big pass through the cycle, you do multiple quick cycles. You build software in small pieces, and after each sprint, you have something to show users, get feedback, and adjust if needed. Agile teams might do a bit of planning, designing, coding, and testing every couple of weeks, continually refining the product. This continuous iteration makes it easier to adapt to new ideas or changes. To summarize the difference, Waterfall is linear and sequential, whereas Agile is incremental and iterative, focusing on adaptability and continuous improvement. No matter which approach is used, understanding the SDLC stages is fundamental for software engineers. It provides a framework that helps teams organize their work and communicate clearly about what needs to happen when. By following the life cycle, engineers can deliver software that meets user needs and maintains high quality, rather than just diving into coding without a plan. Tools and techniques used in software engineering. Software engineers rely on a variety of tools and methods to carry out the SDLC and build software effectively. Let's talk about a few key examples. Programming languages. These are the fundamental tools for writing software. Different programming languages are suited to different tasks, but all of them let humans communicate instructions to machines. Some of the most popular languages in use today include Java, Python, C++, and JavaScript. Each language has its strengths. For instance, Python is known for its simplicity and is often used in data science and web development. Java is common in large-scale enterprise applications and Android app development. C++ is used for performance-intensive applications like game engines or system software, and JavaScript is essential for web development. A good software engineer will choose the language that best fits the project at hand, and often needs to know multiple languages. Integrated development environments, IDEs. An IDE is a software application that provides comprehensive facilities to programmers for software development. Examples include Visual Studio Code, IntelliJ IDEA, or Eclipse. IDEs typically offer a code editor, debugging tools, and other features that help increase productivity. For example, as you write code, the IDE can highlight syntax errors, autocomplete code, and allow you to step through your program to find bugs. Version control systems. When multiple people are coding, it's crucial to keep track of changes to the code. Version control systems like Git are used to manage code history. Git allows engineers to save snapshots of their code at different points in time, compare changes, and revert to earlier versions if needed. It also makes collaboration easier. Multiple developers can work on different features simultaneously and later merge their code together. In fact, Git has become the de facto standard for version control in the software industry. Platforms like GitHub or GitLab host Git repositories online, making it easy for teams to contribute to the same codebase. Project management and collaboration tools. Building software is usually a team effort, so keeping everyone organized is important. Tools like Jira help software teams plan and track their work. Jira is an issue and project tracking system where engineers can record tasks, bugs, and new features as tickets, and move them through workflow stages. It's especially popular in Agile teams for managing sprints and backlogs. Using such tools, everyone knows what everyone else is working on, deadlines are clear, and progress can be visualized. Apart from Jira, teams also use communication and documentation tools like Slack, Confluence or Wikis, and Trello or Asana. Automated testing frameworks. Testing can be very time-consuming if done manually, so software engineers often use tools to automate it. Selenium, for example, is a popular framework for automating web browser interactions. It allows testers to write scripts that automatically click buttons, fill forms, and verify results on a website, just like a human user would, but much faster and more reliably. By using Selenium or similar tools, engineers can run a full checklist of tests every time the software changes to make sure nothing broke unexpectedly. There are many other testing frameworks too, tailored to different types of testing. Automation is key in modern software development. It ties into a practice called continuous integration where every code change is automatically tested by a server, ensuring that the software remains stable as it grows. Other tools and techniques. Software engineering encompasses a lot more. There are design tools for creating wireframes and mockups, configuration management tools like Docker, build tools like Maven or Gradle, and deployment tools that help release software to servers or app stores. There are also methodologies like DevOps, which blends development with IT operations to streamline the building, testing, and releasing of software. DevOps involves tools for automating deployments, monitoring software in production, and quickly iterating on feedback. While a beginner doesn't need to know all these immediately, it's good to be aware that software engineering is not just about writing code, it's about using the right tools and practices to manage complexity and collaborate effectively. In summary, tools and techniques are the engineer's toolbox that makes creating software feasible and efficient. They help manage complexity, improve quality, and allow teams to work together smoothly. Part of being a software engineer is continuously learning new tools, since technology is always evolving with faster, better ways to build software. Career opportunities in software engineering. One exciting aspect of software engineering is the wealth of career opportunities it offers. Software engineers are in high demand across many industries, and this demand is only growing as our world becomes more digital. In fact, in the United States, software development-related jobs are projected to grow 17% from 2023 to 2033, which is much faster than the average for all occupations. This means there will be hundreds of thousands of new software jobs in the coming decade. Not only are there many jobs, but they also tend to be well paid. For example, the median salary for software developers in the US was over $130,000 per year as of 2024. Let's look at 5 common roles in the field of software engineering. Software developer, software engineer. These titles are often used interchangeably. People in this role design and code software applications. They may work on anything from mobile apps to web services to desktop programs. A developer typically works as part of a team, writing code to implement features and fix bugs. They also might collaborate on designing how the software should work. This is usually an entry-level to mid-level role. If you enjoy programming and building things, this is the core career path to pursue. Software engineers need strong programming skills, but also the ability to solve problems and think logically. Every piece of software you use, whether it's Instagram, Microsoft Word, or the software in a smart refrigerator, was built by software developers/engineers. Systems analyst. A systems analyst is a bit different from a pure coder. Analysts focus on understanding business or user requirements and figuring out how to design or improve software systems to meet those needs. They act as a bridge between the non-technical stakeholders and the technical team. For example, a systems analyst working in a hospital might talk to doctors and nurses to gather requirements for an electronic health records system, and then work with the software developers to translate those requirements into a technical plan. They often analyze existing systems and processes and identify where improvements can be made. This role is great for people who like problem solving and communication, since you need to understand both the technical details and the business context. Software architect. Think of this person as a master builder for software. A software architect is an experienced engineer who designs the high-level structure of a software system. They make big-picture decisions about how the software should be built, which technologies to use, how the components will interact, what the overarching design patterns will be. For instance, if a company is building a large e-commerce platform, the architect might decide how to split the system into microservices, choose whether to host on cloud services, decide on database solutions, and ensure the system can handle a large number of users. Architects need a lot of experience because their decisions affect the work of dozens of developers and the success of the project. They often mentor developers, review code for adherence to the design, and tweak the architecture as requirements evolve. This role is suited for those who have deep technical knowledge and a strategic mindset. Quality assurance, QA, or test engineer. QA engineers focus on testing the software to ensure it meets quality standards before it reaches users. They design test plans, write test cases, and use tools to find bugs and verify that new features work as intended. In some teams, developers and QA roles are blended, but larger organizations often have dedicated QA professionals. This can be a good entry point into software for those who enjoy breaking things and have an eye for detail. DevOps engineer. Another role that has become common is the DevOps engineer, who works on the infrastructure and tools that allow software to be built, tested, and deployed rapidly. They are experts in things like cloud services, automation scripts, and monitoring systems. Their goal is to streamline the development pipeline, ensuring that code goes from a developer's laptop to a running application in production as smoothly as possible. DevOps engineers might set up continuous integration/continuous deployment pipelines, manage servers, and respond to performance or security issues in applications. These are just a few examples. The software field is broad. Other titles you might encounter include UI/UX designer, data engineer or machine learning engineer, security engineer, and many more. One advantage of software engineering careers is flexibility. Software engineers can work in virtually any industry: finance, healthcare, entertainment, education, you name it, because every sector uses software. They can also work at different types of organizations, from large tech giants to small startups, or as freelance consultants. If you're considering a career in software engineering, it's also good to know that the field values continuous learning. Technologies change fast, so engineers are always learning new languages, frameworks, or tools. This means the job stays interesting. There's always something new to master. Many software engineers find the work rewarding not just because of the pay, but because of the creativity involved and the satisfaction of building something useful. There's a real thrill in seeing something you coded being used by thousands or millions of people. Finally, career progression in software engineering can lead to roles in technical leadership or management. A common path is starting as a junior developer, growing into a senior developer or tech lead, and then potentially into engineering management. Alternatively, one can remain on a technical track and become a principal engineer or distinguished engineer, where you're the go-to expert for solving the hardest technical problems. In short, software engineering offers a dynamic and promising career path. Whether you love coding, designing systems, ensuring quality, or managing technology projects, there's a role for you. And with the relentless growth of technology, skilled software engineers will continue to be highly sought after. If you enjoy learning and problem solving, and want to have a hand in creating the future of technology, software engineering is definitely a field to consider. We've covered a lot of ground in this video, from the basics of what software engineering is to the detailed stages of the software development life cycle, the tools of the trade, and the exciting career paths available. The key takeaway is that software engineering is an essential pillar of modern technology. It ensures that all the software we rely on is carefully planned, well built, and maintained for quality. By understanding the SDLC and using proper tools and practices, software engineers are able to create the reliable and innovative software that powers our world. If you're inspired by what you learned, remember that software engineering is a field open to continuous learners. There are plenty of resources to start your journey, from online coding tutorials to university programs. You don't have to become an expert overnight. The important thing is to keep learning and stay curious. Thank you for watching. We hope this video has been informative and sparked your interest in software engineering. If you enjoyed the content, please hit the like button, share this video with others who might find it useful, and subscribe to our channel. Don't forget to check out our other videos on different branches of engineering and technology. Happy learning, and see you next time.